It's 3 o'clock, so let's get started. So I know yesterday was a lot of information. We covered a lot of topics. So are there any questions about what we were able to cover yesterday? So all the things about dynamic programming. Sorry, not dynamic. For divide and conquer, the 4 problems that we were able to discuss. No questions? All right, so assignment 3 is out, and obviously assignment 2 was due yesterday. Assignment 3 is out. So just to go over it again, you'll be making a Sudoku checker and a solver in Python. So given the table of 81 integers, 9 by 9, what you'll be doing is checking whether the Sudoku grid is a valid grid according to the rules of Sudoku, and then given an incomplete grid, try to solve a Sudoku puzzle by filling in the appropriate values so that at the end it's a valid grid. Second part is validating magic squares, which has a different set of rules, but instead of being strictly 81 integers for Sudoku, it could be any perfect square number of integers given. So you'll have to determine what the number of the n by n square is because you're given n squared integers there. And then the final part is just generalizing the 8 queens problem we talked about a few lectures ago by having any n by n grid specified to you as input, and then I want you to create a valid n queen solution so that no queen on this grid can attack any other queen. Okay? So are there any questions about assignment 3? So it's due on Sunday night, I believe. So 5 days, I think that's fair for this. So I've had several people ask me about projects. So are there any questions about projects in general? So the proposal for your project is due on Monday night. So assignment 3 is Sunday. The proposal's due Monday. So obviously you can work with a group. You can choose a topic on here. So I've already had someone request a topic already. So if you want to reserve a topic, please do it as soon as possible. Or you can do a topic that's not even listed on here if you find something that's also interesting. Okay? So are there any questions about projects? No questions? All right. Cool. So we started talking about this last time, but I figured it would be a good idea to start from the beginning, from scratch, and talk about probably one of the most important things in computer science. It comes from math more so, but it's extensively used in computer science. So graphs, if you learn nothing else from this class, I would say graphs is the major thing you should learn from this class. So what are graphs? They are basically a set of 2 things. So you're given a set of vertices. I have plenty of examples, so you'll see a few. Vertices and edges. So what are each of these? V is a set of vertices, so you can think of these as just points in a plane, or however you want to think of this. And E is a set of edges. So what an edge is corresponds to two vertices. So basically, with one edge, you're connecting up 2 vertices. And there are some graphs that are called hypergraphs, which have hyperedges, which have more than two or more vertices associated with an edge, but we don't concern ourselves much with that, just for completeness. So there are 2 types of graphs, undirected and directed. So if I just say the word graph without any specifier on it, I mean undirected. So what does undirected and directed mean? So I said that each edge associates 2 vertices together. So if I say undirected, it doesn't matter which way you traverse the edge, because we're going to be doing traversal algorithms, so it doesn't matter which way you traverse the edge in the undirected case. But for directed graphs, the direction matters. You can't travel in the backwards direction. All right? for terminology, sometimes directed edges are called arcs. And sometimes instead of saying E for edges, it's called A for arcs. And the way you write this is as an ordered pair XY. So the notation here means vertex X and vertex Y with a directed edge from vertex X to vertex Y. All right? Undirected edges, we just call them edges, and you write them as unordered pairs. So the curly braces mean unordered. So it doesn't matter if you write XY or YX. And in terms of a graph, you can consider this as a directed edge from X to Y and Y to X. So you can think of this, every undirected edge, as two directed edges, right? Because you can travel this direction or the other direction. So, but sometimes we don't consider that, sometimes we do. But the main idea of graphs is try to model some particular network, be it a computer network, social network, whatever the problem may be. And what you want to figure out is, what is the structure of the graph? Like, how are the vertices related to each other? How far are vertices away from each other? So I'm sure many of you have heard of how every single person on Earth is within 6 people of you. So that's basically a giant graph where every person is a vertex, and an edge is made between you and every single person you know. And so the goal of that graph is, what is the longest sequence, what is the longest path? I haven't defined path yet, but it's what is the longest path in the graph, right? And so if you believe that that statement is true, that you're 6 away from every person, then the longest possible way from any vertex to any other vertex is 6 edges, right? So that's just one application, but there are many more. We want to sometimes know, is the graph connected? So maybe there are some vertices that aren't connected to the rest of them. Sometimes you want to know whether there's some edge in the graph that if you remove it, it disconnects the entire graph. So that's what's called a bridge. So you can think of that as some large subset of vertices right here, and then another subset, and then this one little edge connecting them. So sometimes you want to know that. So you can consider that edge as being really important to that graph being connected, right? Sometimes you want to know what is the shortest path from where I currently am to everywhere else in the graph. Sometimes you want to know, are 2 vertices connected at all, right? Is there a way from one vertex to another? What is the longest path from here to here, from here to there? What is the shortest path? What is the average path length? Many possible questions you can ask here. So here's an example I pulled off the web of a really large graph. So you can see that the way it's laid out, that there are obviously many vertices. So vertices are the little dots here. I'm not sure what the colors mean, but maybe it's some coloring, I don't know. But the vertices are laid out so the ones on the outside edge have relatively low influence on the network, right? They aren't connected to many other vertices. Like, say for instance, this vertex and this vertex only have one edge corresponding to each of them. Whereas the ones in the middle have a lot more edges being connected. So in some sense, those are the more important vertices in the network. And so when we finish this material and get to the next part of the graphs material, we'll talk about how do we determine algorithmically what vertices are the more important ones with respect to some metric. So maybe we have like that edge between those 2 giant sets example, but we have maybe one vertex in the middle. So it's like giant component with one edge to one vertex and then another edge to this other giant component. So you can consider how important that vertex is, because if you remove it, then this becomes disconnected. You may also consider an importance metric to be how close is a particular vertex to every other vertex, right? If it's like the closest vertex overall to every other vertex, maybe we want to consider that as important. And so importance metrics what are called centrality metrics are very important to analyzing graphs. Yeah.
On that previous one, are the ones on the edges that don't connect to anything else, or are those the undirected ones?
This is an undirected graph because each of the edges, when you want to draw a graph, say a directed graph, you draw the actual arrow on the edge.
Which way it's directed?
Which way it's directed, yeah. So if it's just a line between two vertices, then that means undirected. Yeah, I should have said that. Yeah, but if it has the actual arrow, so I'll see if I can find an example. So, yeah, directed graph. Because this is actually important. So, if you look at this directed graph, you see that there are obviously arrows on each edge. So the head of the directed edge is where the arrow is. That means that's where it's pointed to. That's the direction you can go. And so that's called the head. The tail of the edge is where it begins. So that's the vertex you can leave from, and the head is where you can go to. So
F would be the head and A would be the tail.
Of that particular edge, yes. Of that one edge, yeah. So I can so I can travel from E to F, but I can't travel from F to E.
Gotcha.
And of course I can add a directed edge from F to E if I wanted to, but as the graph is, I can only travel one way. But if these were undirected edges, I can travel both ways. Yeah, good point. Any other questions? Yeah.
The vertices that only share an edge between itself and one other vertice, should those still be considered part of the graph? Right?
Yes. So sometimes we only consider connected graphs, right? So I'll define connectedness in a second, but it makes intuitive sense. The graph is connected. But sometimes we have what are called components. So we may have a very large component in the center, so all the vertices in there are connected to each other. But sometimes we have smaller ones, like these little two vertex components, like out here, where each of these these components of two vertices only have one edge between them. Okay? So we should consider that sometimes, but sometimes we don't consider that. I love plugging my thesis into this area. So what I did for my thesis was I studied the Arctic sea ice concentrations, and I modeled it as a graph. So in that problem, I only considered the largest component of vertices because there were many smaller components, like a couple thousand of these little two vertex components. So for simplicity, I only considered one component to make the analysis a little easier. And it had over half the vertices, so any conclusion I can make about this one large component could be said about the larger one too. Not the larger one, all of the vertices. All right, so any other questions? All right, so some applications of graphs. So the main idea behind graphs is trying to define some relationship between different objects. So you can model this as relationships between people, between, say, road networks, between cities, like Google Maps does, many different ways for describing relationships. So social networks is a really huge application here. So what you do is you model each vertex as a user, right? And when you say on a social network that they friend each other, you create an edge between those two vertices. And so to have a distinction here, Twitter, since you can follow someone but they don't have to follow you back, it's a good idea to model that as a directed edge, right? Because I can follow the follow path, if that makes any sense. If we can follow someone, we go in that particular direction. So it makes sense to have a directed edge there. Whereas for Facebook, since when you friend someone successfully, they are friends with you too. So in some sense, it makes sense to have a undirected edge there because I can travel either direction, right? Because you're friends with each other.
So
yeah.
So you know how on Facebook they have
you have this whole list of people that you might know.
Mhm.
Would that count as like the outer edges then? Because you're not technically, I guess, connected with them, but they're still part of your
Mhm.
your I don't know, group.
Right. So one thing that we're going to be talking about with graph traversal is what is called the frontier. So you can define this this component of friends that you know, and then you can look at all of each of your friends' neighbors that aren't currently in the network. So that's basically like if you have the set of users that are your friends is one layer in a sense out of there. So so basically you can consider that as edges to be made because they're not your friends yet. But you could consider those as edges in some sense. Like those are the connections that could possibly be made, right? And that's actually really important at advertising, right? Trying to figure out what vertices will reach the most amount of people that currently aren't in your network, right? If you want to get as little as work possible to reach as most people as possible, that would be really good from an advertising point of view, right? So yeah, Facebook should have undirected edges. Another one is solving puzzles. Everyone knows what a Rubik's Cube is. So you can model a Rubik's Cube kind of solver graph where you can say a vertex is every possible state that the Rubik's Cube could be in. So like a solve state is one vertex, and then each of the possible turns represents a different vertex, and so on and so forth. And then you create edges between the vertices. Such as like if you make one 90-degree turn, that'll be an edge between each of those two configurations of the Rubik's Cube, right? And so we may want to know, what is the fewest possible moves that from any configuration will reach the solve state, right? So I have a particular configuration of the Rubik's Cube, and I want to solve the Rubik's Cube in as few moves as possible. And so that's some particular number. And then I want to know what are, in a sense, the hardest configurations of the Rubik's Cube, which means what is the longest of these shortest sequences, of these shortest paths, right? So in a sense, these are the configurations which take the longest number of moves to solve. And this is what is called the diameter of the graph. So among all shortest paths between all vertices, give me the length of the longest one. So that's what's called the diameter. We won't be going into the diameter too much, but it's an interesting area for how much time it takes to compute that. For 2x2x2, there are, how do I phrase this? There are configurations which do require 11 moves to solve, but there are none that require 12. So basically the hardest configuration takes at most 11 moves. And for the 3x3x3, I think that was solved 3 or 4 years ago. So it's relatively recent. It is 20. So there are configurations of the normal Rubik's Cube that take 20 moves to solve, but there are none that require 21, right? And so that's what's called God's number. So if you want to search for that, and it's actually pretty interesting how that works. But for, yeah, you have a question?
So that's considered the maximum of the shortest paths.
Yeah, that's the longest possible shortest path in this, if you model this as a graph, which I don't think they did, but if you did model as a graph.
Why the longest shortest path?
Right. Right, so let's just look at this one at a time. So we can look at a configuration of the Rubik's Cube, right? And I want to know what is the shortest number of moves that I can make so that I get to the solve state, the solve vertex. So that would basically be the shortest path through this graph until I get to the solve state, right? So that may be 15, I don't know, some number. So I want to know, among all possible non-solved vertices, what is their shortest path to the solve state? among all of those, and I want to take the maximum of them. So this is essentially saying, what is the one that requires the most amount of moves? And it happens to be 20 for 3 by 3 by 3. Does that make sense?
Yeah.
I know this is a little confusing sometimes to wrap your head around, but all I'm doing here is illustrating applications. We're not going to be getting into this material. I actually don't even think we're going to get into it at all, but if you want to get to it for a project, you can, but I'm just highlighting applications. Okay. For a project idea, this is a paper that was released, I guess now 5 years ago, that gives an asymptotic bound on what the size of this diameter will be for Rubik's Cubes. And it turns out to be a little bit less than n squared. So if you want to figure out why that's true, then you can. You can also look at how they were able to determine this 11 and 20 number, because determining that was actually very complicated. So what they did, just as a little bit of a glance, obviously if I just take a Rubik's Cube and then just rotate the cube, don't do any moves on it, it's the same cube, right? And it also doesn't matter if I make one move on one side, it's essentially doing the same thing as doing a move on the other side for certain configurations. So they were able to reduce by a lot the number of total possibilities for each of the configurations by a very large number, I think. And what they did after that was, once they reduced it, then they just did a computer search over all of the ones that remained. And so that's essentially how they were able to do that. Questions on applications?
Nobody's challenged it. Like I said, I did it in 21 moves.
Well, obviously there are ways to get larger than 20 moves for any particular configuration. Even one that's one away, I can do like 50 moves out and then 50 moves back.
Sure.
Yeah, right. So the key here is what you would say is, I want to prove that this configuration I have requires 21 moves. So that's essentially saying, no matter what possibility I can do, I cannot get to that solved state in 20.
Gotcha.
Yeah, so that's a much harder question, obviously.
Yeah.
So the yes answer is easy, the no answer is hard. All right, cool. So now we're going to talk about some terminology of graphs so that we can get on the same fundamental level about what I'm talking about with respect to graphs. So we talked about, in that large graph picture I gave, those little two component vertices. So there are two vertices with exactly one edge in between them. So what we talk about there is the degree of those vertices. So in terms of those vertices that have only one edge between them, since one edge is touching each of those vertices, the degree of each is exactly 1. They only have one edge. But in general, you talk about what is the degree of any vertex, the number of edges that touch it. And that's for the undirected case, but for the directed case is a little different, because we have some edges that go out, some edges that come in. So we usually talk about, for directed graphs, the in degree of a vertex is the number of edges coming in, and out degree is the number of edges going out of that vertex. So just as pictorially, these are all undirected graphs. So there are some graphs which are what are called a cycle. The upper left one, which has only one vertex but still has an edge from coming out of itself back into itself, an undirected edge. So that's what's called a loop in a graph. We have other graphs. So each of the ones at the top have degree 2 because there are only 2 edges connecting each of the vertices. And the ones down here have degree 3 because there are 3 edges that connect to each vertex. Questions about degree? Yeah.
Is the degree number determined by the most amount of edges connected to something, or the...
I talk about degree of a vertex. So every single vertex has a degree. So I may have some vertices that have only degree 1, some maybe they have 0, maybe some have 100.
You have though graphs with degree of r equals 3
Yeah.
in there. So what if you put another point on one of the side edges and connected a fourth line to the center one?
Yeah. So
Everything would have 3, but the middle would have 4. Would that be the graph would be a degree of r equals 4?
so you're saying like for this graph right here, I add some vertex right here, and where do I connect it to?
To the very center.
Yeah. So I only connect that vertex to the very center, right?
Mm-hmm.
So since this vertex, and this vertex are unchanged, they still have degree 3. The vertex I added only has one edge connecting it, so it has degree 1. And since I added 1 to this middle one, it has degree 4 now. So I have some that have 1, 3, and 4.
Okay.
Okay? So it depends on each of the where the edges go. All right. So some other things. So a subgraph is just take a subset of the vertices. So you can either have the entire graph as a subgraph, or a smaller version of the graph, or even no vertices at all. That's totally allowed. And an induced subgraph is basically you only keep the edges that are within the subgraph. So just as an example, I think this is, no, that's not the Peterson graph. So I have a graph on the left-hand side, and so a subgraph is I want to take out the middle 5 vertices. So that's what I do, so that's a subgraph. But I also only want the edges that still exist within those 5 remaining vertices, the inner 5 vertices I take out. So that's an induced subgraph. Yeah?
Why would you ever use the edges without the vertices? Isn't every subgraph an induced subgraph?
I'm actually not sure why, but I think there are some applications where you only keep one of the endpoints of an edge. But most of the time, pretty much all the time, we talk about induced subgraphs, yeah. Because it's more intuitive, right? Because we think of edges as being 2 vertices connecting each other. But yeah, induced subgraph. All right. Another thing, I talked about paths earlier, but just as more information about what they are, they are a sequence of vertices that connect each other in a row, right? So you can't have, you're traveling along some sequence of edges and then pop off to somewhere else and then continue going. It must be a continuous sequence of vertices that are connected to each other. And we sometimes talk about simple paths, which are ones that don't repeat vertices. So here is a simple path. So, can you see it? Yeah. So this is a simple path because it is a path, obviously. It doesn't jump anywhere else because each of the edges connects each of the next vertices in a row. And it's, what is an example of a path in here that's not a simple path? Well, you can think of, since a simple path does not repeat vertices, you can think of a path that's not simple to be one that repeats a vertex, right? So you can think of that as going to some vertex, then coming out, then coming back, and then keep going, right? So an example of that would be, say, 5, 0, 4, 11, 5, 0, 4, 9, because that does a repetition of several vertices. So that would not be a simple path, but this one is simple. So sometimes we actually do make the distinction between paths and simple paths. Any questions about that? All right. I talked about connected before, but we say that a graph is connected if informally there is some way to get from every vertex to every other vertex, right? There's not some vertex that's out somewhere in the middle of nowhere, not connected to anything. Yeah, so in order to be connected, you must be able to get from any vertex to anywhere else, right? And I have an example of this. So, in a clique, some people pronounce it clique, but I actually say clique. So what that is a group of vertices where every possible edge exists between them. So just as an example, here is a connected graph, right? there's no vertex in here for which I can't reach it from anywhere else. Like 1 can go to 6, 3 can go to 5 via some path in the graph, right? So this graph is a connected graph. And the ones that are highlighted in red, that is a clique because between those 3 vertices, every single possible edge exists, right? 5 to 1, 1 to 2, 2 to 5, there are no more edges. You can actually talk about what are called multi-edges, which are edges that can exist, multiple edges which can exist between the same 2 vertices. So instead of just this one edge, there could be another edge that goes between them. So I'm not actually talking about multi-edge graphs. The ones that aren't multi-edge are called simple, but here basically every possible edge exists between these vertices. So can anyone find a 4 clique? So this is what is called 3 clique, which means there are 3 vertices. Is there a 4 clique here? Well, every single possible edge, does every single possible edge exist between those vertices? Well, let's just pick the example. So there is a 2 clique. Oh, you can actually think every edge is a 2 clique, right? But the more interesting case is when you get to 3 and more. The 3 case is sometimes called a triangle, but there actually isn't a 4 clique here. Oh, so why is that true? Well, in order to have a 4 clique, we have 4 vertices that must connect every other vertex, right? What is the degree of all the vertices in a 4 clique? 3, right? Because I'm not thinking of those that connect to itself, so no loops there. But so they connect to every other vertex. Well, from any vertex, there are 3 others. So we should be able to find 4 vertices that have degree 3 here. But so 5 is a candidate, 2 is a candidate, and 4 is a candidate. But there are no other vertices of degree 3. So therefore, there cannot be a 4 clique here. Okay? Yeah. If there were an edge from 4 to 2 and 3 to 5, then it would certainly be a 4 clique. And when I said that there must be a vertex of degree 3, 4 vertices of degree 3 there, I meant of degree at least 3, right? Because I can just discard the edges that I don't want. So here are some examples of cliques. So these are actually what are called the complete graphs for obvious reasons, right? So the complete graph called K2 on 2 vertices, K3 on 3, K4 on 4, etc. So what that means is every possible edge exists there, right? So yeah, so you can generalize this obviously to more vertices, but these are the complete graphs. And so sometimes an important question is, what is the largest clique in a graph? That might be an important question you want to know. Like, say, here's a funny example that some of you may have heard from me. Let's say that you want to be a really good host by throwing a nice party for graduation or something. So you want to invite as many friends as you want to your party because you want it to be successful, right? But you want it to be a celebration because it's a graduation, right? You don't want any fights to happen. So you want to make sure to invite as many people as possible, but so that each friend is a friend with someone else. So that's basically the clique problem, right? Try to find the largest subgraph of a graph that you're given such that it's a clique, right? So find the largest clique in a graph. That's actually a very computationally hard question. We actually don't know if there's an efficient algorithm for it. So hopefully if we get to that material, you'll see why that's true. But so cliques are actually very important for analysis. So yeah.
If you put an X in the middle between 2, 3, 4, 5, would 1 be included in that clique?
It depends what you mean by included. So there definitely is a 4 clique here, right? So you're asking whether there's a 5 clique.
Could be, yeah.
Yeah, but 1 isn't connected to 4 or 3 directly. There is a path to them, but there's not a direct relationship. Yeah, but if there were, it would be a 5 cleave. Yeah, any other questions? Okay, cool. So I've mentioned cycle a few times. So when we mentioned paths that are not simple, we had this behavior where we repeated a vertex by doing what is essentially called a cycle. So a cycle is just a path that starts and ends with the same vertex, right? And sometimes we want to talk about simple cycles, which a cycle that only repeats the first and last vertex, right? So you could have a cycle that comes out and then comes to the same vertex, then comes out somewhere else, and then comes back to the same vertex. So it repeated that starting vertex 3 times instead of twice. So sometimes we talk about cycles versus simple cycles. All right. So can anyone tell me of a simple cycle in this graph? So I must start with the vertex and go out and then come back to where I started. H, G, D, H. Yeah. So that would be a 3 cycle because it's of length 3 edges and 3 vertices.
What about the entire outside?
Yeah, the entire outside. So A, B, C, E, F, G. You can actually go back to D, H, A. Yeah. So there are actually many cycles in this graph, both non-simple and simple. So sometimes a question that I'm actually interested in for my research is, given a graph, try to count the number of cycles in the graph. Sometimes you want to know the number of subgraphs that have some number of cycles inside of that subgraph. And so cycles are actually very important for research purposes and trying to understand the structure of the graph.
So
Yeah.
it's really, just so take H, G, D, H, for example.
Mm-hmm.
Does it really matter which one is the start?
Yeah.
In all the vertices, basically, they can make it come back to itself, right? So it doesn't really matter.
Yeah, there are many starting and ending ones. I'm not really usually concerned about where you start and end. What I'm usually concerned about is whether there is a cycle or not. Yeah.
When finding cycles, are you using backtracking, or is there a
When we do the graph traversal algorithms, we'll encounter a part about cycles. Yeah. So informally, what you can think of that is start somewhere in the graph. It doesn't matter if it's undirected. Then just branch out. If you ever get to a point to where you've seen a vertex before, you found a cycle. Right? If you just keep branching out and then mark vertices as you see them, if you see a marked vertex at any point, you found a cycle. Right? Because you got to that point already, and then you came out and then you discovered it again. So that's a way of finding cycles in a graph. Any other questions on cycles?
And you said a vertice that goes in itself is cycle too, right?
So like one vertex that has an edge from it
From itself.
going out from itself to itself.
Yeah,
So there are several competing definitions. So usually that's what's called that's considered a loop. So it's not usually considered a cycle. So what is usually considered is cycles of length at least 2. Yeah, so you must go out and then come back at least to one other vertex. Yeah. Any other questions on cycles? Okay. All right. So something that you've seen before and from 205, but I'm just going to generalize it a little. So a tree is a graph that has no cycles. So when I talked about this branching out thing, where if we found a way to get back to ourselves, to a vertex we've seen already, then we found a cycle. So a tree is basically you branch out and then you never see a vertex you've seen before, right? And so we've seen trees, say in 205, called binary trees, but I'm using a general definition of trees. So a root is usually called just some vertex of the tree. It actually doesn't matter what a vertex I choose here, but as long as it's just some special designated vertex. A leaf is a vertex in this tree with degree 1. So here is just some vertex that's only connected to one other vertex, and that's it, right? So if you think about, like, say, a binary tree where you want to find a particular element, you go down the tree, and then if you want to, say, insert an element at a particular place in the tree, if you get to a leaf node and you haven't found an element that exists yet, then you can insert it, right? So leaves are important. One of the projects, which is about context-free grammar, so anyone see that project? So context-free grammars are especially important in programming languages, and they're usually used to figure out whether a program is syntactically correct before compiling it and other things. So what those are for are, say, when you want to verify if a program's correct, you look at the leaf nodes of what is called the parse tree constructed using that program. And what you want to know is, can you get a parse tree with all the leaves being the characters of the program? Okay? So leaves are really important in trees here. So here's an example of a tree, and here's an example of another tree, which is binary tree. So you can actually think of a binary tree as a directed graph because you traverse down the tree, but you can't traverse up, right? And so what is the in degree of vertex 8 for the directed graph here? The in degree? 0, because there are no edges coming in. So you can think of the root of a directed graph, a directed tree, to be the only vertex with in degree 0, right? And what about the leaves here? What are their out degrees? 0 also, right? So you can think of, in a directed tree, the vertices that have out degree 0 are the leaves of the tree, right? So that's actually quite an efficient algorithm. So I can just iterate through the list of vertices. If the out degree, say, is 0, then I know it's a leaf, right? So that I don't need to do some special traversing algorithm here. So for directed graphs, it's easy to figure out what the root is. But for undirected graphs, I can make any node to be the root. So for example, I can make, say, vertex 4 to be the root. So if I make vertex 4 to be the root, what are the leaves of that tree now? So 1, 2, 3, and 6. Yeah. What if I made vertex 2 to be the tree? What would be the leaves there? Oh, 1, 3, and 6. Yeah. It's pretty simple how to do that. But being able to figure out whether a graph is a tree is actually pretty important because that's just detecting if there's a cycle in the graph. And it turns out that many of the algorithms that we find important are a lot easier for trees than a general graph. So having the case for trees is actually very nice because you know that there are no cycles. And something else important, you can actually prove that if you have n vertices in a tree, it has exactly n-1 edges, right?
N-1 what?
Edges, yeah, because you can just do a count. If you have 2 vertices with 1 edge, 2 vertices, 1 edge, 2 vertices, yeah, just subtract 1, right? And then you can just prove by induction that it's n-1. Any questions about trees? Yeah.
So what considers the right one a binary tree?
Because what considers it to be a binary tree is that the out degree of any node is at most 2.
Oh, okay.
Yeah, because some have out degree 1s, obviously 0, but some have 2. But say if I had another vertex over here that 8 connected to, then the out degree of 8 would be 3, so it wouldn't be binary anymore. Right, so a binary tree just means a directed tree with out degree at most 2 for every vertex. And in some sense, this is connected. But in another sense, like you can't get from vertex 13 to back up to vertex 8 because it's directed. If it were undirected, it would be connected. So that's what's called weakly connected. I think I had talked about it, but all right. Yeah, here. So we talked about connected for undirected graphs, which means I can get from any vertex to any other vertex. Just this one slide, then we can take a break. So, but now I want to talk about directed graphs because here we have, we can get from one vertex to another, but we can't get from that vertex back, right, because it's directed. So if we have a strongly connected directed graph, that means that for every pair of vertices, we have the same property as undirected, right? Because no matter what vertex I traverse from to get to any other vertex, I can go back, right? But we may have this case where I have a way to get from one and not the way back. So that's what's called, maybe I have it, no. All right, I actually don't have it, I should add it. You may think, well, if we have strongly connected, we also have weakly connected. So weakly connected means that if you convert all the edges to be undirected, it's a connected graph. So here, if we make all the edges to be undirected without any direction on the edges, then it's obviously connected, right? Because there's no vertex outlying anywhere.
Would it make it strongly connected?
Strongly connected is only for directed graphs. So I know this is really confusing, but just the word connected by itself is only for undirected graphs. And then strongly and weakly are for directed. Yeah, yeah. I know it's really confusing, but so yeah. If you think of it like the adverbs on the adjective, it's kind of like directed for graphs. It's like it's another word to be added to it. All right. So another thing about connectedness. So a bridge is is assigned to an edge. If you remove that particular edge, the graph becomes disconnected in some sense. Okay. So can anyone tell me of a bridge in this graph? There are actually many of them. A G to N is a bridge. What's another one?
PQ.
A PQ, A, B, D, E. Yeah, all of those are. So you can think of that as any vertex with degree 1. If you remove the edge that's connected to it, it automatically becomes disconnected. So that's already a bridge. But there are non-trivial bridges like G to N, because G and N obviously have degree more than 1. Okay? All right, I think that's a good time to take a break. All right, welcome back. Let's get started again. So what I wanted to do for the rest of the time, because I overloaded you with a whole bunch of terminology and stuff, I thought it would be cool to do an example of how to use graphs in Python. So any questions on any of the terminology we've covered so far? Yeah.
You can talk about weights of the graph.
The what?
Weight of the graph.
Oh, I didn't do weights yet. Yeah. But I will talk about that eventually. Yeah. Any other questions? All right. So how do we represent graphs? Well, there are really two main camps of thought of how to do this. So the first one is using what are called adjacency lists, right? So for what you do here is you maintain either a linked list or an array, whatever you want, but you maintain one for each of the vertices. And what the list contains are all of the vertices for which it's connected to, right? So like for this graph, let's just say I wanted to look at the linked list for, say, vertex G. So it's connected to vertex C, K, and N. So that linked list or array or whatever you want will contain the references or strings or whatever you want to C, K, and N, right? So it only concerns what you're connected to directly. But the key here is that you maintain one for each of the vertices. So that might be a little bit difficult, right? Because you may have a lot of vertices, and I don't want to have to maintain all of this all at once. So another camp of thought is, well, what we can do is we can just make an indicator of whether, say, G is connected to N or G is connected to A, right? So we can say G is not connected to A, right, directly, and G is connected to N, right? So one thing we can do is squash all of the possible linked lists together all at once into what is called an adjacency matrix. So just graphically, so what an adjacency matrix is you make a matrix, so an n by n matrix, where n is the number of vertices. And so each of the entries of the matrix is indexed both by the columns and rows by each vertex. So in this graph right here, I have 6 vertices. So I'll have an adjacency matrix of size 6 by 6. So the way that the matrix is structured as is that the ijth entry, so like right here, the first row, second column, that will be 1 if the row vertex is connected to the column vertex. So what does that mean? That means that if we're looking right here, that means is vertex 1 connected to vertex 2? Like from 1 to 2, since this graph is directed. So we see, oh yeah, 1 is directly connected to 2. But we should see that in this graph, because it's directed, 2 is not connected to 1, right? So that means we should see in the 2, 1 entry, we should see a 0, which we do. So you do that for every pair of vertices in the graph. You look at whether they're connected or not, and then you fill in this matrix of 0 or 1 depending on whether they're connected or not. Oh, oops. So any questions about that? So, so there are pros and cons of each. Well, the pro of using the adjacency matrix is that it's a lot easier to look up, right? Because array lookups happen in pretty much constant time, right? I just specify the index of the row and the column, and I get the value right away. But for an adjacency list, what I need, I can look up the list in constant time, but even if I keep the list of vertices it's connected to sorted, it still takes logarithmic time to access it via binary search. And if I'm really terrible at this, I could possibly have linear search time there, right? But, so what is a con of using the adjacency matrix? Well, as I talked about earlier, with trees, they have n-1 edges for n vertices. So that means how many entries are in this table for n vertices? Well, there are n rows, n squared, right? So what is n, pretty much order n, versus n squared? A huge difference, right? So a ton of these entries are going to be 0. So that's what we call a sparse matrix. So only a very few number of the entries are going to be non-zero. So I'm wasting a lot of space there. But for the adjacency list, I'm not going to be storing all those zeros, right? Because I only consider the vertices that I'm connected to directly, right? So there's a pro and con of each, depending on what type of graph you're going to be working with. Yeah.
Is B, that's the adjacency list?
Yeah. So this is a linked list.
Is how that works.
Yeah. So the way it's graphically depicted is each of the rows in a sense corresponds to a vertex. So vertex 1, 2, 3, 4, 5, 6, and it's depicted here as a linked list, but it could be an array depending on what you want. So the way it's depicted is the element that's connected to, and another element that 1 is also connected to.
So ones would be stored there?
It's the value of the vertex has to be stored there because I want to look up the vertex value. Because if I just stored 1, then how do I know what vertices it's connected to?
Yeah.
Yeah. So the name of the vertex is stored there. Okay. And obviously this end symbol means the end of the linked list. But obviously we have ways to do that with arrays, so it's easier to do with an array, but it's depicted here as a linked list. Yeah. Any questions about this? So who wants to maintain n linked lists? Doesn't that sound fun? Who wants to maintain a JCC matrix of size n by n? Does that sound fun? So we could do that, but we have a better way. So pretty much always with Python, there's a better way. So there's an awesome there are actually many packages that do this, but the most popular one for modeling graphs in Python is called Network X. So what Network X does is you can model a graph with it. Okay? And so what is usually done is you import the module. This is not a standard library, so I'll show you how to get this module. But what you usually do is you import the module, and what people usually do, because you don't want to say networkx dot function name, you just say import it as this alias nx. So then I can just say nx dot whatever. So here we can create a graph, nx.graph. So at the start, this is just an empty graph, no vertices, no edges, nothing. And we can add nodes with a particular label. So I can say add node 1 or then integer 1, or I can say spam or anything I want to attach to it. I think it has to be an iterable or it's hashable or something like that, but I can add any label to a node that I want. I can add edges, so add edge, there are many forms of add edge, but here it can take 2 arguments, so it's the from and to arguments. So from vertex to vertex. So by default, as I've said before, graphs are considered undirected unless you specify that it's directed. So this is an undirected graph here. So if I wanted to look at what this graph looks like, it would be 2 vertices with an undirected edge between them. Okay, and the first vertex, the vertex labeled 1 to vertex labeled 2. So even though I didn't say add node 1, add node 2, when you say add edge, it adds those vertices for you. So technically, I should have 3 vertices here, because I have one that says spam as the name of that vertex, a vertex labeled 1, vertex labeled 2, and 1 edge between 1 and 2. Okay? Pretty simple?
So those vertices are now called 1 and 2?
Mm-hmm.
It doesn't matter if there are different types of vertices then? Because obviously the first one's going to be a string and the other two is a
No, it's just a label. So it's really just a string on the back end. It has no difference on what the structure of the graph is. It's just a name for being able to differentiate different vertices. And then I can call g.nodes. So in the literature, sometimes we call vertices nodes. So the particular function name here is g.nodes, which returns to you a iterable with all the nodes of G. And so you can get properties like the degree of a vertex, you can get any sort of information you want. And then I can just print the list. So it'll print to me 1, 2, spam. So those are the vertices here. And then I can do, as you may expect, you can do the same thing with edges. And it prints to me, since it's an unordered pair because it's an undirected graph, actually I don't know why that is. It just returns to you a tuple for each edge that it corresponds to. So the one edge in there is 1 and 2, 1 to 2. All right, so now let's do a really cool example that I like. So how many of you actually use Facebook? So what Facebook wants to do is, and many people who use Facebook, is how do people relate to each other on Facebook? How many friends are you away from some person? So like the example that was mentioned earlier about the frontier of the people that you may possibly know. So those are just the friends of your friends, just one level out, that happen to not be your friends. So all sorts of questions you want to ask. So there are many data sets available about Facebook Twitter, anything you want. Do I still have it? Yeah. I can actually show you and share it with you. Let's see. Yes, I have it. So there's a library by a big data set collection by Stanford. So they have data sets about Facebook, Twitter, Google+, all that stuff. So you can analyze like the structure of a particular group of people. So obviously, the example that we're going to do is this Facebook one. So obviously, 4,000 nodes. That really is the entirety of Facebook, obviously, right? So and only 88,000 edges. So this is only a really small subset of the entire Facebook site. Yeah.
That because everybody's in a sense connected in certain ways, that's the majority of Facebook.
I was kidding. There
okay.
there are over 1 billion people on Facebook.
I was gonna
yeah.
say, okay.
Yeah, it's not even close. So even doing like the adjacency lists, one, because obviously a billion by billion matrix, that's completely intractable. So because think about it, like what is the maximum number of friends that you could have on Facebook? It is actually about 5,000. I think it is 5,000. So the degree of any vertex is at most 5,000. So 1 million of vertices with at most 5,000 edges each. So that's actually a very sparse graph, right? Because 5,000 compared to 1 billion is very tiny. So doing the adjacency matrix representation is very intractable. It's going to be very sparse. But even if you do the adjacency list one, you're going to have 1 billion of linked lists or arrays, and each one's going to have 5,000 elements. So even 1 billion times 5, let's actually do that calculation. So 1 billion times 5,000. So that's 5 times 10 to the 12th. So let's just say that we can index each of these with a 32-bit number, right? So this is, I can just multiply by 32 to get the number of bits. You can actually save a few here. So that's the number of bits that I need, divided by 8 for bytes, divided by 1024 for kilobytes, megabytes, gigabytes. So, and if we divide by 1024 again to get terabytes, this would be over 18 terabytes to store this, which is insanely huge. Like even the thesis that I worked with only had like 30,000 vertices, and that took several days to do some calculations I wanted to do, because some of the algorithms that are known only have n to the 3 running time. So this is just absolutely intractable. So a really cool thing is to figure out how does Facebook maintain information about like their graph? How are they able to figure out some information about like what people are doing, how people are connected on their network? But anyway, back to here. So the example that we're going to work with is this Facebook data set. So it's an anonymized set of connections. So what it is basically is a very large file that has, for each line, it has 2 values. So the first value is this person is connected to this person, right? So say whoever vertex 0 is connected to vertex 1, right? 0 to 2, 0 to 3, all the way through the file. And so what I want to know is what are the degrees of all the vertices in the graph? Like, so I want to figure out which of these people is connected to the most number of people. What are the vertices in here that are connected to the least amount of people, right? So that's something I want to know. So I already said that network X is not part of the standard library, so we'll need to import it. So what's an easy way to import a library or to get a library that's not part of the standard library? Pip3 install. So pip3, for those who don't know, is the main way to install a package that's that actually is the official way to install a package that's not currently in the standard library. So I'll make this a little bigger. So pip3 install means that I want to install some library, and then after here you specify the library that you want. So the library that we're using now is called Network X, so I just type in Network X. So then it'll go out to there. Yeah, so you may see something else because I have Network X already, I think. So I just want to, you may see something else, but you can install packages this way. Okay, so let's look at this. So I started off already with saying open this file as this file pointer, and then just read the lines of the file. So what do the lines look like? The lines look like is basically user 1 user with a space in between user 2, right? So we can just iterate over each of the lines, and then since they're separated by a space, how do I differentiate those two users? Starts with an S. Almost. I want to split by a space, right? So so I want to say the split. How about two users is line.split. Scroll up to what? I haven't gotten to there yet. It was a matplotlib import, but it's to visualize it, but I haven't gotten there yet. Yeah, so, but since we can do unpacking, I can just unpack the two values because I know each of the lines in the file has exactly two elements. So I can actually just say u comma v. So u will be the first user and v will be the second user. So I know that my graph must be undirected because it's Facebook, right? Because you're friends with each other, right? So before this, I better create a graph. So I'm going to let G be nx.graph. So if I wanted a directed graph, what you do instead is di graph. So what that means is directed. People actually do say digraph, but here we'll actually just do graph because it's undirected. All right. So now I want to make an edge between vertex u and vertex v. And I said that even though in our example for network X, even though I didn't say add node 1, add node 2, it created those nodes already. So I can just say add edge u and v. So I just say g.add edge uv. And so let's just make sure we got this right. So let's just print the number of edges in the graph. So if we run this, Python 3, what do I call it? Read. So it'll go through the file. So we have 88234. We should expect that. And that's exactly what we have. So we actually did successfully read the file and make edges as necessary. Cool. So now I want to get something more interesting. Oh, so any questions about this at all? All right, so as I said, we can look at the degrees of each vertex. So the way to do this is, it's not a method on the graph itself, but through the network X library. So what you can do is you can set a variable to be degrees, which is nx.degree of g. So what this returns is a dictionary, and what is in the dictionary is obviously, since it's a dictionary, key value pair. So the keys in here are each of the vertices of the original graph, and the value is the degree of each vertex, right? And so what I want to look at is, I don't want to necessarily look at the vertice names themselves. I just want the degrees, the values of each of the key value pairs. I don't want the keys. It doesn't matter. So does anyone know how we can just get the values of everything in the dictionary all at once? It's actually since this is a dictionary, you can call them values the values function. So what that returns is all of the values in the dictionary. So you can either do two things. You can either do that, or you can do keys, or you can actually do another one which is called items. So what items is an iterable, and it'll return to you a key value pair as when you iterate over it. But here I only want the values. Questions on that? Okay. And what I want to do is I'm going to be eventually plotting this. So I want some kind of pattern to appear. So I don't want some like this vertex is 10, then this one has 4,000, and this one has 30, 100. Like I don't want some random pattern. I want to have all the vertices that have low degree at the beginning or at the end, and then have it go up, right? So obviously now I just want it to be sorted. So I just feed this to sorted. So these are all the degrees I want. And now, like I said, I want to plot this, right? But is there a plotting library in Python? Not by default. So there's another library that we'll be importing called matplotlib. Any of you use MATLAB? Yeah, so painful, right? Want to use Python instead to do the same functionality? Yeah, please, yeah. So there's a pip library called matplotlib. So it's just a lot of plotting functions that you can get all at once with Python. All right. I tried to uninstall this, but it says that we already have it. Oh well. All right. So we downloaded it from pip. So now I want to import that library also. So what we do is import matplotlib, but there's only one particular module that we want from matplotlib, a submodule called pyplot. So pyplot is basically a bunch of methods that allow you to plot either a function if you want, or a scatter plot, histogram, whatever you want. So, and then since I don't want to type matplotlib.pyplot all over again, I'm going to do another alias. So plt is going to be pyplot, basically. All right. So what I want to do here is I want to plot these values. So in order to feed it to PLT, I need to have a list of values to feed to it, or I can just feed an iterator to it like I do with sorted. So here I just call plt.plot degrees. I think that's it. Let's just see what happens. Python 3, read. Did a figure appear? No, right? So what's going on? So what happens here is that we didn't actually show the plot. So if we call plt.show, I think this would work. All right, yes. So it gave us a figure, right? So we can zoom in and do whatever we want with it. But what do you think happens when I try to exit out of here? It just closes, right? So in order to make that figure again, I need to regenerate the entire figure. And I might be able to save it that way, but maybe I just want to save the figure right away, right? That might be a good idea. So there's a method called savefig. So plt.savefig, and then you pass in the name of the file name that you want to save it to. So I'm going to save this as degrees.png. And you can make this JPEG or whatever you want. All right, so It's still going to show because I still have plt.show, but it saved this file degrees.png, which is on my hard drive now. So, and it's nice they actually formatted my axes nice and everything. That's pretty cool, right? But we can do better. Actually, let's just run that again. You can see that there aren't any names associated with the axes, right? Like if I wanted to say use my figure in a paper or something, I don't have a title here, right? Or axis labels. So you can actually set labels here if you want to. So what you do with this is you call plt.ylabel, and you can guess that means the label of the y-axis. So that means the degree, because the value of what's being plotted is the degree of each vertex. And plt. You can call x label if you want, but since the order doesn't matter, I don't think I really do need x label here. But you can actually set a title to your plot. So you can say plt.title sorted degrees. And then if we run again, it'll give us a title and y-axis label. Yeah.
Does the save fig function, does that automatically save over your previous?
Yes.
Okay.
Yeah. Unfortunately, yeah. So you'll have to figure out a way to differentiate that every time. But so maybe you can use like a Unix timestamp or something to differentiate it. All right. But let's look at that figure again. Let's look at this in a bigger window. So what's a major problem with this? Actually, two major problems.
Scale.
Scale is a problem, right? Well, what scale is wrong?
They're not scaled to each other.
Well,
The x and the y scale are.
well, I don't. Well, look at the right before it makes the big jump. It's like at 200-ish, right? I don't have much information on what happens below there. I only have information about up there, right? So what can I do about that? How would you approach this? Reduce scale, right? So one thing that's pretty common with when you see things like this is to make the logarithm of the y-axis or the x-axis, right? So what we can do then is just make the y-axis be the logarithm. So instead of plotting the degrees now, I'm plotting the log of the degrees. So for these really large values, it's going to be scaled down to be relative to each other instead of just this really large value at the end. So what we can do then is we can set the scale of y to be log. So y scale, log. And you can also do x scale here if you wanted to. So if we run this again, we get a much nicer-ish looking figure, right? Cool. What's another problem? If we zoom in, what happens?
Stairs.
Well, you're not going to really get rid of that problem because of the way log works. Because each of the values that are given to it are all integers. So every vertex along one line is going to be the same. So you're not going to get rid of that problem. But what's another problem that you see? It's pretty pixelated, right? Right, so maybe we can increase the resolution of this a little bit. Okay, so the way to do that is before you plot, you call plt.figure. And what that does is it sets up in the background a figure for which, it actually does that for you by default. But when you do plot, title, y-scale, you set the properties of the figure. And then when you do show and save fig, it like shows the figure that you made and saves the figure. But here, if I want to actually explicitly give it arguments, then I need to do it right here. All right. So the way to do this is you don't feed, for some weirdo reason, I don't know why, you don't feed it like the number of pixels across, number of pixels up and down. So the way to do it is you feed it dots per inch. So you say, I want 80 dots per inch, and then you feed the number of inches across, number of inches up. So it actually can be quite useful if you're working on, say, a poster for like a presentation or something, and you know how big your figure's going to be, and you know the dots per inch of that, so you can just feed it here. So what you do here is you feed it to the number of inches across and down to a named argument called fig size. So here I'm going to provide the number of inches across, number of inches down. So here I'm going to make it 20 and 12, but you can make it anything that you want. All right, so if we run this again, it should be higher resolution. And I think it is. So if we zoom in, it's definitely better, but it's not ideal, definitely ideal, but it's definitely a lot better. All right. So any questions about how we were able to do that? Yeah, so there are tons of methods in NetworkX. For all the graph search algorithms, there are algorithms to, say, give a particular vertex and give me all the distances to all other vertices. Yeah.
Sort of off topic, but how is it doing it behind the scenes? You know, like in 205 you program the array list to figure out what's just an array that has all these methods. Like, how is that creating a graph behind the scenes that it's still able to maintain it, you know?
So what's the number one way to figure out what something does? Documentation. Exactly. So NetworkX, documentation. I actually don't know if it says it, but I know that NetworkX does allow you access to their source code. So let's see, latest release. Oh, what's there? I don't know if the documentation's on here. Yeah, maybe we can. Okay, yeah, maybe. Yeah, I'm not really used to doing documentation this way. I always just go online and look, but you can definitely look up. I guess the documentation is there, but let's see. Creating a graph. I actually don't know, but I'm pretty sure they do an adjacency matrix. I'm pretty sure, because the way you look up edges is you look up. Say I had a vertex 1. You look up vertex 1, all of the vertices it's connected to by doing the array index operator. But obviously we could overload this to be whatever we want because we have operator overloading. But I'm pretty sure that's how they do it for NetworkX. But it'd be interesting to know how they actually do this. Yeah, because from here you can actually index into each of the lists for each of the vertices. But I don't know for sure. Good question though. Any other questions on any of this? I think that's enough for today, so let's stop here.